Hello everyone, welcome to today's class. Myself Dr. Sohail Rana, and we are studying electromagnetic fields and transmission lines. Welcome to today's session. Today we will study about Gauss Law and the applications of the Gauss Law. So let us begin with the theory and the logic of Gauss Law. This law is all about the flux and its relevance with the charges. So let us consider this 3D diagram as a reference. Here we can see one toy example is given where one sphere can be seen. Now imagine this sphere is electrically isolated. That means it is not electrically connected with anyone, and this is a neutral charge sphere. So of course it's looking like a globe, but it is not a globe. This is just a toy example to understand the concept of flux. Now this is a sphere which is electrically isolated and there is no charge. It is electrically isolated, and if we bring a positive charge bar near to this sphere, so there is a bar or a conductor, we can say, where there is a positive charge and we are bringing it near this sphere, then what is the observation? What may be the possible output of this setup? That we have to discuss. Now miraculously, what we observe that when we bring this electrically isolated sphere near a charge, then it also gets equal and opposite charge on its surface. So what happened? How these charges crossed a free air or free space or a dielectric and converted into equal and opposite charge. That is the essence of our subject. Now this is something we have to discuss in this chapter. What is that something which crossed the medium and it reached to the sphere? That is part of our discussion in this chapter. So this something is defined as flux. So it is called as, say, electric flux. So Faraday and Oersted before him, they all experimented on some force lines, some invisible force lines which are not visible to our eyes. These are invisible force lines say we have some kind of invisible force lines. These force lines cannot be seen by the naked eyes. This something which is crossing is defined as electric flux psi. So this is part of our subject, electric flux. So this chapter particularly discuss about Gauss law and its application. They are solely depending upon the flux. So Faraday's experiment, what Faraday did, he did experiment on two spheres, and what he observed, suppose when we remove that bar from that place, then the bar we have taken away from this place which had some positive charge, but automatically there was development of equal and opposite charge on the sphere. So what is this? This is transfer of charge. Either we consider positive charge or negative charge in terms of electrons, they cannot cross in free space. Electrons cannot jump in the air and they cannot travel to other places, but they take some other form and they travel in that some other form. That other form is nothing but flux phi. What is another difference between the flux and charges? Now here we can see we have one more diagram here. Two spheres can be seen. One sphere is a sphere 1 with positive charge, another sphere is there with negative charge. Now this positive sphere and negative sphere, both of them don't have any electrical connection between them. They are electrically isolated. So in that case, what should be the observation? There should not be any transfer of any kind of charge. That is the basic definition of a circuit. If we consider a circuit of a capacitor, what is capacitor? Capacitor is nothing but two charged plates separated by some dielectric. So if we consider this example of capacitor, say one plate there are positive charges, another plate there are negative charges. Now if we connect other passive elements in the circuit, for example say R is connected, and this whole thing we will connect with a battery or voltage. Now this circuit is technically, practically correct circuit. But what is definition of a circuit? A circuit says that there must be a closed path. But if capacitor ends are open, then how it can be a closed path? It cannot be a closed path. So in that case, we get some sort of charge transfer, but that charge transfer will be in the form of displacement current. That is not the conventional current. What flows in this circuit is the conventional current, conduction current. But here this something flies, that is nothing but electric flux. So whatever amount of charge is present here, that will be passed to the next plate, and that charge will be equal to that flux. So we can say in general this charge Q is nothing but equal to the flux crossing that area. So this is the basis of the Gauss law also, and Faraday also did the experiment. So he considered two spheres, say one sphere at the center of the say coordinate system, and he considered another sphere of another radius on the outer shell, and he gave say some negative charge on the outer sphere, and both were electrically isolated. That means there was no electrical connection. They were electrically isolated. And after some time, what he did, he removed that sphere. And what he observed, to the surprise, is that there was creation of equal and opposite charge on the inside surface. All these cases are indicating one thing only, that even if electrons or charges cannot move in free space, but they take some other form to travel across the medium, that something is defined as electric flux. So here we are talking about the something which is electric flux. So let us move and discuss it in more detail. So let us discuss the relation between the electric field and the flux and the relation between them. Here we have, in this entire subject, there are four important vectors. These four vectors are capital E, capital D, capital B and capital H. As we know, these all four vectors are vector which operate in space. They are part of electromagnetic wave. Out of these, two are related to electric field, these two are related with magnetic field. Then there are two intensities, these electric and magnetic field intensities, and there are two densities, electric and magnetic flux density. So here we are talking about the flux. So all about flux. So as we have flux, there will be density of flux. This density of flux is, if it is electrical, it is called as d bar. So d bar is electric flux. We should also remember the units for these four parameters. The unit for E is volts per meter. Unit for D is coulombs per meter square. Unit for H is amperes per meter square, and unit for B is Webers per meter square. Now if we focus on the units of these two, what we can observe, these two, say B and D, they are related with cos per area. Any kind of density, what we say, any cause of any density can be given by cos per area. Now if we talk about the d bar, now its cause is some flux. Say flux is creating flux density, so cos will be flux itself. So d bar will be equal to, say, psi. Now area depend upon our setup. So if we consider a sphere, the area of sphere we can take as 4 pi r square. This is the area. Now this one is magnitude. This is the magnitude. Along with this magnitude, we have to add one direction. So say usually we take that direction as AR cap. So say this will be the direction. So magnitude and this direction all combinedly make this as electric flux density. So this is the relation. Now if we consider the logic of our previous discussion, what we are saying, say psi is nothing but Q. How much charge is present, same will be crossed in the form of flux. So if we have to modify this expression, what we can write? We can write flux in we can write charge in place of flux. So same expression, by keeping psi is equal to Q, we can write as d bar is equal to Q by 4 pi r square into AR cap. So this is the form of electric flux and its density. So now this unit can be justified, where coulomb is unit of a charge, and meter square is some surface area. So like this we get the unit of D as coulombs per meter square. Then let us discuss it in the form of Gauss law. Now Gauss law states the same thing. Now what Gauss law states? Gauss law says that any charge Q enclosed in any area will be equal to the flux crossing through that area. So from this he can say that the density of D bar is equal to psi or Q upon 4 pi r square. Now Gauss law is applicable to Gaussian surface. Gauss law talks about one Gaussian surface. Gaussian surface is nothing but any place, any surface where we can apply the Gauss law. So Gaussian surface is any place where we can apply Gauss law. And what is Gauss law? The total charge enclosed by that surface will be equal to the flux crossing through that surface. So flux, if it is in more quantity, we call it as D. So this D is also related with electric field intensity. We know the relation D is equal to epsilon E, where D is the flux density and E is the electric field intensity. Both of them are related with each other by epsilon, that is nothing but permittivity of the medium. So let us see more about Gaussian surface. Now this image we can consider as one example of Gaussian surface. Now what we can observe here, that flux lines are coming out of the surface. If we consider this sphere and the differential surface in the form of some chunks of small differential surfaces. So for that differential surface, any differential surface, if we consider out of entire surface, and the magnetic flux density is coming out of it, D bar. So it may be normal or with some angle. But if electric field intensity and D, if we consider electric field intensity, will always be perpendicular to the surface of the source charge, for example. So if we have a positive charge, then for positive charge the electric field intensity will be always perpendicular to the surface, that is normal to the surface. Something like this. Now here in this case we are considering D bar as normal, and if we are able to apply Gauss law on this surface, then we will call it as Gaussian surface. This is just some sample example surface. It may have different shape also, different size also. So what is take out for this? If we are able to apply Gauss law here, that means we can say D bar is equal to psi by 4 pi r square into AR cap or in other words we can say d bar is equal to q upon 4 pi r square into ar cap. Now this area is for this sphere. It can be differential surface also, or it can be any other volume also, but here in this case we are considering it as a sphere, so we are taking the example of sphere. So in other form, if we take the basic definition of the flux density, what we can say, any kind of density, say d bar is the density, it will be equal to directly proportional to the cos, and cos of it is say differential flux. Now we are not considering the sphere, now we are considering any other general surface of any other shape. And from this total surface S, we are taking small differential surface and we are studying how much is the electric flux density. So now in this case we will not write the value of sphere, simply we can write it as say differential surface ds, because it is not necessary that it is a shape of volume only. If we consider volume, then we will consider dV, but now right now we are considering one general shape surface. It may have any shape, right? Okay, so this is d bar equal to d psi by ds bar. Along with that we have to add the direction, so it can be written as ar cap. From here what we can say, d psi is equal to d bar dot ds bar. So this is differential flux enclosed in this differential surface. Now if I want to find out the flux covered on the total region, the entire region, then what we can write for that, say we can change it to, say from here if I want to find out for the total flux, say total flux psi, so RHS we have to take the integration. Now right hand side will be integration, but which integration? Double integration, because right side we have a surface. So for this surface we will have some integration, its value will be given as double integration. So right side we have to take double integration, because two axes are involved. There may be one x axis and say y axis, right, two dimensional system, and here we have to take integration of this term, that is d bar dot ds bar. So this is the ds form. Now if we consider a closed Gaussian surface, then we have to take some integration here. So with this session we will stop here, and we will meet you again in the next session. In next session we will discuss about the applications of Gauss law. Till then, have a good day. Thank you.